http://1.1201 created cache control no cache pragma no cache content type application/sn Charsit equals at 8 location http://localhost 8000/API/contacts/6 content negotiation HTTP servers often have multiple ways to represent the same resources. The representations can be based on a variety of factors, including different capabilities of the client or optimizations based on the payload. For example, you saw how the contact resource returns a vCard representation tailored to clients such as mail programs. HTTP allows the client to participate in the selection of the media type by informing the server of its preferences. This dance of selection between client and server is what is known as content negotiation, or CNEG. Caching as we learn it in method properties on page 14, some responses are cacheable. In particular, the responses for GET and HEAD requests. The main benefit of caching is to improve general performance and scale on the Internet. Caching helps clients and origin servers in the following ways. Clients are helped because the number of round trips to the server is reduced, and because the response payload is reduced for many of those round trips. Servers are helped because intermediaries can return cached representations, thus reducing the load on the origin server. An HTTP cache is a storage mechanism that manages adding, retrieving, and removing responses from the origin server to the cache. Caches will try to handle only requests that use a cacheable method. All other requests with non-cacheable methods will be automatically forwarded to the origin server. The cache will also forward to the origin server requests that are cacheable, but that are either not present in the cache or expired. Twist defines a pretty sophisticated mechanism for caching. Though there are many finer details, HTTP caching is fundamentally based on two concepts: expiration and validation. Expiration: a response has expired or becomes stale if its age in the cache is greater than the max minimum age, which is specified via a max age cache control directive in the response. It will also expire if the current date on the cache server exceeds the expiration date, which is specified via the response expires header. If the response has not expired, it is eligible for the cache to serve it. However, there are other pieces of control data. See caching and negotiated responses on page 19 coming from the request and the cached response that may prevent it from being served. Validation: when a response has expired, the cache must revalidate it. Validation means the cache will send a conditional GET request. See conditional requests on page 13 to the server asking if the cached response is still valid. The conditional request will contain a cache validator, for example, an if modified since header with the last modified value of the response and / or an if none match header with the response's tag value. If the origin server determines it is still valid, it will return a bodiless response with a status code of 304 not modified, along with an updated expiration date. If the response has changed, the origin server will return a new response, which will ultimately get served by the cache and replace the current cached representation. Serving stale responses: HTTP does provide for caches to serve stale responses under certain conditions, such as if the origin server is unreachable. In these conditions, a cache may still serve stale responses as long as a warning header is included in the response to inform the client. HTTP Cache Control Extensions for Stale Content, by Mark Nottingham, Proposes new cache control directives. See cache behaviors on page 20 to address these conditions. The stale while revalidate directive allows a cache to serve up stale content while it is in the process of validating it in order to hide the latency of the validation. The stale if error directive allows the cache to serve up content whenever there is an error that could be due to the network or the origin server being unavailable. Both directives inform caches that it is okay to serve stale content if these headers are present. While the aforementioned warning header informs clients that the content they have is actually stale. Note that RFC 5861 is marked as informational, meaning it has not been standardized. Thus, all caches may not support these additional directives. Invalidation. Once a response has been cached, it can also be invalidated. Generally, this will happen because the cache observes a request with an unsafe method to a resource that it has previously cached. Because a request was made that modifies the state of the resource, the cache knows that its representation is invalid. Additionally, the cache should invalidate the location and content location responses for the same unsafe request if the response was not an error. ETAGs an entity tag, or ETAG, is a validator for the currently selected representation at a point in time. It is represented as a quoted opaque identifier and should not be passed by clients. The server can return an ETAG which it also caches in the response via the ETAG header. A client can save that ETAG to use as a validator for a future conditional request, passing the ETAG as the value for an if match or if none match header. Note that the client in this case may be an intermediary cache. The server matches up the ETAG in the request against the existing ETAG it has for the requested resource. If the resource has been modified in the time since the ETAG was generated, then the resource's ETAG on the server will have changed and there will not be a match. There are two types of ETAGs. A strong ETAG is guaranteed to change whenever the server representation changes. A strong ETAG must be unique across all other representations of the same resource. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. A weak ETAG is not guaranteed to be up to date with the resource state. It also does not have the constraints of being unique across other representations of the same resource. A weak ETAG must be preceded with W for example, W/1, 2, 3, 4, 5, 6, 7, 8, 9. Strong ETAGs are the default and should be preferred for conditional requests. Caching and negotiated responses. Caches support the ability to serve negotiated responses through the usage of the vary header. The vary header allows the origin server to specify one or more header fields that it used as part of performing content negotiation. Whenever a request comes in that matches a representation in the cache that has a vary header, the values for those fields must match in the request in order for that representation to be eligible to be served. The following is an example of a response using the vary header to specify that the accept header was used. http://1.1200 OK content type application /JSON. Charset equals at 8 content length 183 vary. Accept cache behaviors. The cache control header gives instructions to caching mechanisms through which that request /response passes related to its cacheability. The instructions can be provided by either the origin server as part of the response, or the client as part of the request. The header value is a list of caching directives that specifies things like whether or not the content is cacheable, where it may be stored, what its expiration policy is, and when it should be revalidated or reloaded from the origin server. For example, the no cache directive tells caches they must always revalidate the cached response before serving it. The pragma header can specify a no cache value that is equivalent to the no cache control directive. Following is an example of a response using the cache control header. In this case, it is specifying the max age for caches as 3,600 seconds 1 hour from the last modified date. It also specifies that cache servers must revalidate with the origin server once the cached representation has expired before returning it again. http://1.1200 OK cache control must revalidate. Max age equals 3,600 content type application/SN. Charsit equals @8 last modified wed. The 26th of December, 2012 220,515 GMT date through. The 27th of December, 2012 010515 GMT content length. 183 For a detailed walkthrough of caching in action, see Appendix D. For more on HTTP caching in general, see Things Caches Do, by Ryan Tomiko, and How Web Caches Work, by Mark Nottingham. Authentication HTTP provides an extensible framework for servers that allows them to protect their resources and allows clients to access them through authentication. Servers can protect one or more of their resources, with each resource being assigned to a logical partition known as a realm. Each realm can have its own authentication scheme, or method of authorization it supports. Upon receiving a request for accessing a protected resource, the server will return a response with a status 401 unauthorized or a status 403 forbidden. The response will also contain a www authenticate header containing a challenge, indicating that the client must authenticate to access the resource. The challenge is an extensible token that describes the authentication scheme and additional authentication parameters. For example, the challenge for accessing a protected contacts resource that specifies the use of the HTTP basic authentication scheme is basic realm equals contacts. To explore how this challenge /response mechanism works in more detail, see Appendix D. Authentication schemes. In the previous section we learned about the framework for authentication. RFC 2617 then defines two concrete authentication mechanisms. Basic. In this scheme, credentials are sent as a base 64 encoded username and password separated by a colon in clear text. Basic auth is conventionally combined with TLS. HTTPS due to its inherent unsecure nature, thus, its advantage is that it is extremely easy to implement and access, including from browser clients, which makes it an attractive choice for many API authors. Digest. In Digest, the user's credentials are sent in clear text. Digest addresses this problem by using a checksum map that the client sends, which the server can use to validate the credentials. However, this scheme has several security and performance disadvantages and is not often used. The following is an example of an HTTP basic challenge response after an attempt to access a protected resource. http://1.1401 unauthorized. www authenticate basic realm equals web API book. As you can see, the server has returned a 401, including a www authenticate header indicating that the client must authenticate using HTTP basic. get/resource http:/1.1. Authorization. Basic QWXBY2U6/1HZ2 GIFT/1 PC2GGT3 Zoidal. The client then sends back the original request, including the authorization header, in order to access the protected resource. Additional authentication schemes. There are additional authentication schemes that have appeared since RFC 2617, including vendor-specific mechanisms. AWS Authentication. This scheme, used for authenticating to Amazon Web Services S3, involves the client concatenating several parts of the request to form a string. The user then uses his AWS shared secret access key to calculate a MAC hash message authentication code, which is used to sign the request. Azure Storage. Windows Azure offers several different schemes to access Windows Azure storage services, each of which involves using a shared key to sign the request. Hawk. This new scheme, authored by Aaron Hammer, provides a general-purpose shared key auth mechanism similar to AWS and Azure. The key is also never used directly in the requests. Rather, it is used to calculate a MAC value that is included in the request. This prevents the key from being intercepted, such as in a man-in-the-middle MITM attack. OAuth 2.0. Using this framework allows a resource owner, the user, to delegate permission to a client to access a protected resource from a resource server on her behalf. An authentication server grants the client a limited use access token, which the client can then use to access the resource. The clear advantage here is that the user's credentials are never directly exchanged with the client application attempting to access the resource. You'll learn more about HTTP authentication mechanisms and implementing them, including OAuth, in chapters 15 and 16. Conclusion. In this chapter we've taken a broad brush approach at surveying the HTTP landscape. The concepts covered were not meant for completeness but rather to help you wade into the pool of HTTP and give you a basic foundation for your ASP.NET Web API development. You'll notice we've included further references for each of the items discussed. These references will prove invaluable as you actually move forward with your Web API development, so keep them in your back pocket. On to APIs. Chapter 2. Web APIs. There's more to Web APIs than